Hello, everyone. Good morning, or evening, afternoon, whatever time you're watching this video. This is Gary here, um, building a roguelike in Rust. Um, so last time we left off with a map that kind of looked like this, um, where we can basically just walk around these rooms and corridors. Um, there's not much to it, just generating some rooms, corridors, and a bunch of walls on the outside. So without further ado, let's drop into the actual text here of the tutorial. It says, we have a nicely drawn map, but it shows a whole dungeon. That reduces the usefulness of exploration. If we already know where everything is, why bother exploring? This chapter will add a field of view and adjust rendering to show the parts of the map we've already discovered. It'll also refactor the map into its own structure rather than having just a vector of tiles. This chapter shows the code, starts with the code from chapter 4. Okay, so guys, I already did this refactor. Did off camera because I forgot to start the camera. But really the refactor is, let's change these into public functions. Let's add a struct for the map, right? Um, change these into public functions inside of a map implementation. Um, and literally move everything into it, changing the changing the signature of the methods here, because they used to take in a reference suitable, a mutable reference to some vector of tile type, right? Um, and so, anywho, with that, since we're changing them into an implementation struct, these are basically classes, and they take mutable self now, right? Um, and then new map rooms and corridors, all of that changed, right? So since that changed, we needed to change the implementation of player.rs. I'm assuming we're gonna eventually refactor player as well, but um, we changed the implementation here. Anytime that we had to try to move the player, we had to use map, right? We had to fetch map instead of it was fetching the vector before. Now we're fetching the map. Um, and we had to use map dot xyidx now because that's actually part of the map implementation. Um, what else changed? Inside of main.rs, um, this ECS is the world, right? Um, so now what we're doing here is um, we have to run systems, do our player input call, which this may actually be backwards because player input, actually player input should be fine. No, it calls try move player. So if we do anything, any kind of movements before the player is actually initialized, so we'll change that real quick. We'll actually put that below. Um, uh, oh, that's just game state. That's fine. Okay. Sorry, I was kind of confused a little bit, but if we look at all of this, we have to fetch our map, right? Because we have to draw our map. So we fetch our map rather than the vector, and we draw map.tiles rather than, again, that vector, which map.tiles is pretty much that vector, right? Um, and then we have our main function, which again does the same stuff that it did before. It's just it's creating a new map, right? Using map instead of just calling the function directly in a say map.rooms center now, and then yeah, I think that's pretty much it. We're inserting our map into ECS, and everything is good, right? So Anywho, with that, let's move on. It says we'll keep the map related functions and data together to keep things clear as we make an ever more complicated game. The bulk of this is creating a new map structure and moving our helper functions into its implementation. Okay, so that's that same code as before, pretty much. I didn't copy or anything like that, so um, there's changes in main and player too. See the example source for all the details. Really, all I did here whenever I did this change is I looked at the method signatures here and moved my methods in, tried to run, and fixed all the build errors until eventually I had a game that could build. The Rust build system does a fairly good job at telling you what's wrong. Um, Other languages, it's kind of bad to really depend on that a lot because other languages they don't have that good of an error detection, right? Um, so says there's changes in main and player 2. See the example source for details. This has cleaned up our code quite a bit. We can pass a map around instead of a vector. If we want to teach map to do more things, we have a place to do so. Perfect. The field of view component. Not just the player has limited visibility. Eventually, we'll want monsters to consider what they can see too. So since it's reusable code, we'll make a viewshed component. I like the word viewshed. It comes from the cartography world. Literally, what I can see, what can I see from here? And perfectly describes our problem. We'll give each entity that has a viewshed a list of tiled indices that they can see. In component.rs, we add. Okay. So, oops, we're gonna derive component, and I don't think we need that there. And we're going to say pub struct viewshed pub visible tiles equals vec rltk point. I'm going to again move this point up to this use statement. That way I don't have to type it all out every time. I don't think I'm going to type it out often, but it's good to have it up there. Pub range I32. Perfect. In main.rs, we tell the system about our new component. We've done this a few times before. So CS register, yeah, and we'll say viewshed. Whoops. Perfect. Lastly, also in main.rs, we'll give the player a viewshed component. So here's our player. Give it width, shed, say visible tiles, vec new, a new empty vector, and range, we'll say 8 tiles for now. Okay, so now we can build, and if we just hit the run button, everything should work just the way it's been working before. Nothing has changed. Perfect. A new system generic viewshed. Okay, so before we, yeah, okay. A player is getting quite complicated now. That's good. It shows what an ECS is good for. A new system generic viewsheds. We'll start by defining a system to take care of this for us. We want this to be generic, so it works with anything that can benefit from knowing what it can see. We create a new file, visibilitysystem.rs. Okay. So create a new Rust file, system. All right, so we're gonna use specs prelude Catch it. Yep, mod. And we'll pub use visibility system. Alright, so we're going to use specs, prelude, everything, use super, viewshed, and position, obstruct, visibility system, MPL, and then this weird syntax, a system, a. I really don't know what that A is for. For visibility system. Type. I hope that one day I will be able to understand what that is. System. Okay. Why have an extra set of those? But alright. Type system data. Yeah, we'll just write storage. Again, I don't know what that A is. Viewshed. And I need a comma here. This is a different parameter. Or it's a tuple. Different variable in a tuple. Right, storage dot va position. Be good. And then we'll do fn run. Run takes a mutable reference to self. And it takes in this this tuple of mutable viewshed. Whoops. Position. Self. System data. So this isn't a mutable reference. I think it's a mutable copy. And then this is a immutable copy, right? Or I don't know how that works. So it'd be interesting to find out. Hopefully they explain it. For viewshed and position. So we're not referencing this here quite yet. We are creating new keys or new variables within local scope here, and we'll say in, and then this should be, yeah, so that right there is referencing what's above. And then we have the position. That's all passed around. They join. All right. Now we have to adjust the run systems and main.rs to actually call the system. Yes, yes we do. And where is that run system? Self.run systems. Oh yeah, it's right there. All right, so let mutable visibility. Vis.run now. Self.ecs. ECS maintain. Okay. We also have to tell main.rs how to use the new module. This doesn't actually do anything yet, but we've added a system into the dispatcher, and as soon as we flesh out the code, actually plot visibility, it will apply. Okay, so I've already done this. Yeah, I already done this. This doesn't actually do anything, but it will apply to every entity that has both a viewshed and a position component. Okay, yeah, that's fine. Asking RLTK for a viewshed trait implementation. Okay. RLTK is written to not care about how you've chosen to lay out your map. I want it to be useful for anyone, and not everyone does maps the way this tutorial does. To act as a bridge between our map implementation and RLTK, it provides some traits for us to support. For this example, we need a base map and an algorithm 2D. Don't worry, they are simple enough to implement. In our map.rs file, we add the following. Map.s and pull algorithm. It actually used it up the top for us for map. And we'll say fn dimensions self the autocomplete point. We return, because I'm not going to use that return syntax. Point new self.width self.height. Okay, what's the problem here? Trait bound map base is not satisfied. Oh, okay, yeah, we have to implement base map as well for map. All right, it says RLTK is able to figure out a lot of traits from the dimensions function, point indexing, and reciprocal bounds checks. And similar, we use return. We use return the dimensions. Wow, that's a weird sentence. We're already using self.width and self um, height. We also need to support base map. We don't need all of it yet, so we're going to let it use defaults in map.rs. All right, so base map. It implements it already, right? There's really no functions I need to provide myself, I don't think, but it's providing some stuff here as well. So fn is opec, some overrides, right? Self and usize returns a bool. Self.tiles idx as usize. Actually, idx, because it's already a usize, I shouldn't have to cast it to a usize here, right? And I will say equals tile type. And again, this is a return. I don't know why, because it even says it here. This is a usize, this is a usize. I shouldn't have to cast usize to usize. It's already a usize. So, good. I'm just going to skip that. Okay. Is opec is simply returns true if the tile is a wall and false otherwise. This will have to be expanded if and when we add more types of tile, but for now, we'll leave the rest of the trait on defaults for now. So no need to enter anything else. Asking RLTK for a viewshed, the system. So going back to visibility system.rs, we now have what we need to request a viewshed from RLTK. We extend our visibility system.rs file to look like this. Okay, let's not change system data. It's needing a read expect. Map. Okay. Needs to be a comma. And then we say mutable self, mute viewshed, join, system data, data, self, system data, that's fine. And we do let map mutable view shed position equal. This needs to be a comma. Awesome. And I'm going to go ahead and take it upon myself to add some extra formatting there. Perfect. And then we have view shed position, immutable view shed join. Okay, yep, that's perfectly fine. And we say view shed visible tiles clear. Shed dot visible tiles equals field view. Yes. Point position where's x y shed range. Okay. Then this is a weird thing. All right, I'm going to break this down just a little bit. Make it look a little bit easier to read. Tab. Okay. Tab. Yeah. I was trying to remember the key command for it. I think it would have been faster to just not try to use a key command in this case, but okay. So we'll say view shed visible tiles. Wow, this is some weird syntax. P dot x greater than or equal to 0 and P dot x greater than map dot width and P dot y greater than or equal to 0 P dot y. Okay, yeah. Then P dot y map dot height. Jesus, that is some syntax. Okay, let's hope that works. There's quite a bit here, and the view shed is actually the simplest part. We've added read expect a map, meaning that the system should be passed for our map for use. Should pass our map for use. We use read expect because not having a map is a failure. In the loop, we first clear the list of visible tiles. Then we call RLTK field of view function, providing the starting point, the location of the entity from position, the range from the view shed, and a slightly convoluted dereference. Then we get a reference to unwrap the map from the ECS. Finally, we use the vectors retain method to delete any entries that don't meet the criteria we specify. This is a lambda or closure. It iterates over the vector passing p as a parameter. If p is inside of the map boundaries, we keep it. This prevents other functions from trying to access it, from trying to access a tile outside of the working map area. This will now run for every frame, which is overkill. More on that later. And store a list of visible tiles. Okay. So if I hit run, it should. Ooh. Visibility system, what is wrong? Sorry. Okay, yeah, I would expect it to be the same. But now in memory, we should be calculating the visible area of the map. That's awesome. At least the game's not crashing. What I would imagine that we need to be doing next, which it's going to go over that, but I'm going to make a prediction here. We're going to go over to main.rs, and where we're drawing this map, actually this draw map is going to actually take in our visibility, right? That's probably pretty much it. I would actually happens if I did try to pass that in, but um, we'll take a look at that here in just a minute. So let's actually take a look here. The book says rendering visibility badly. As a first try, we'll change our draw map function to retrieve the map and the player's viewshed. It will only draw tiles present in the viewshed. Okay, let's do that. So map.rs, have that draw map function. We say let mutable. Yeah, this is a full refactor, sort of. Move the coordinates. Okay, so let's actually just rename this function here because we'll use it. Fn draw map. It's going to take in ECS world. Whoops. CTX. Oops. And that's a mutable TK. Okay. And something here with world. Our map cannot have anonymous parameters. Oh, oops, forgot a colon. Okay. Let mute viewshed. ECS.write storage, and is looking for that the viewshed component, and then let mute players equals ECS. Dot write storage, and again it's looking for the player component, right? And then let map equal ECS fetch. Perfect. Now what we're going to do is it looks like we're going to loop through our viewshed, right? So for all of our viewsheds, it doesn't care if it's a player, it's just going to say it's player, but it's going to loop through our viewsheds. Actually, in this case, it does care there's a player, but I mean, we could literally probably say or something else here, right? I don't know how that works. Maybe in the future, we'll see. Mute players, mute viewsheds, dot join. Perfect. And we'll say let mute x equal 0, because I'm going to be looping, or I let mute x comma y. Does that work? No, it doesn't work like other languages would. It's weird that we have to let and mute, because let should be able to be mutable anyway. That's weird. Okay. For tile and map tiles dot iter let pt equal point new x and y if viewshed visible tile that contains and pt match tile type dot or x dot set x y RGB from f32 0.5 0.5 0.5. Wonder if I could do just from hex, and that just makes life easier. Let's try from hex. This is halfway through, so 9, so 9, 16, be 8. So 8, 8, 8, 8, 8, 8. And then RGB from hex 0x0. And honestly, RLTK 437. Oh, I need to put the closing. That doesn't automatically happen. As tile type wall ctx.set x y, and this is red green blue. We're going to set the floor to green. RGB from hex, and this will be 0x 00 ff 00. That's red green blue. RGB dot from hex 0x 000 000. And we'll see how this works. Actually, this can just be 0. Yeah, 0 is all the way across. RLTK CP 437. Cool. And then we move the coordinates. It looks like that's after the if view sheds, right? So we'll copy that, move that here. Oh, it's S. I need an S here. There you go. That's probably why that wasn't working before. Okay, cool. And if we hit run here, what happens? Core FFI. Imported that, but whatever. Required by a bound entry. trait bound integer as ref string is not satisfied. RGB.from hex. Oh, so does it have to be a string? Oh, is that what it wants? Try that way. Prefer to be using hex. String. First, the trait. Color conversion error is not be A. Probably. Okay. That's why he's not wanting to use hex. Oh. We may build a library for this, but we'll just RGB from F32. That's weird that they didn't implement that all the way. Wow, that's crazy. Thought I was gonna be nice and just use hex. But no, can't use hex. Can't use hex, that's funny. Map tiles, expected struct, specs world, found struct. Okay, yep, that's fine. We'll do this here in a minute. I think I could just say, do state.world, or is that right? Or self.world. Right, that should be fine. Self.ecx, it's looking for the reference. Cool. So now we have dungeon. That's cool. We can no longer see what the map looks like. All right. Run the example below, cargo run. It will show you just what the player can see. There's no memory and performance, quite awful. But it's there and about right. It's clear that we're on the right track, but we need a more efficient way to do things. It would be nice if the player could remember the map as well as what they see. So one thing that they've left out is actually changing this reference. I think they expect you to know how to do that. But without further ado, let's keep going. Expanding the map to include revealed tiles. To simulate map memory, we'll extend our map class to include revealed tiles. Okay. So we have tiles pub revealed It should be a vec, right? Yeah, vec bool. Right. We also need to extend the function that fills the map to include the new type. Okay. It's just, yeah, done before except for bar. Yeah, it's that new rooms corridor. Our map to include a new type. In new rooms and corridors. Okay, yeah. We can say reveal tiles, the vec, um, false. Yeah, 80 times 25. That adds a false value for every tile. We change the draw map to look at this value rather than iterating the component each time. This function now looks like, okay, so now when we go to draw map, it's going to it's going to look at map, which is fine. It no longer needs the view sheds in the player. I think it could care less about that at this point. I think that was just as an example. And then we say, yeah, we'll change this loop. Have our x and y is 0, 0. For idx tile for in map dot tiles dot iter dot enumerate. Wow, that's a chain, isn't it? If map dot revealed tiles idx and then we'll do that same matching here, right? Whoops. Surrounding match statement. Dude, this is just a switch statement. Why do they change the name of things? Okay. Fine. Yeah. And then in that for, we just go ahead and iterate x and y. Should be good to go. Now let's see what happens. Crashed. What crashed? Alright, it says error. Didn't exist successfully. Some details are omitted. Backtrace. Okay. Yep, there's that main loop hitting. We have map RS 146 and we say map refilled tiles. I have a feeling that we went out of bounds. We have idx tile in map.tiles iter enumerate. Okay. Map.revealed tiles idx. We have our values, that's fine. Coordinates x and y. Some reason here. Duplicate code there, that's fine. No longer. And why effective tile type for that shouldn't be out of bounds. Generating it here. Yeah, that's very strange. They're both the exact same size. Map. Corridors. This is false. Oh, yeah, that's why. They're not exactly the same size. 80 by 50. I don't know why I did 25. Alright. Cool. We have a black screen. This will render a black screen because we're never setting any tiles to be revealed. So now we extend the visibility system to know how to mark tiles as revealed. To do this, it has to check to see if if an entity is the player, and if it is, it updates the map to reveal the status. Okay, visibility system, got it. We'll import a, yep, and then system data. Well, so this is a write expect now. It's going to do entities A, doesn't care what the type is. Write storage, view shed, write storage position, read storage, player. Okay. The run is going to be a mutable self data, self system data. Okay. And then this becomes a mutable map. Then we need view shed position player. All right, and then here say for ENT view shed position and entities join. Okay, and it says view shed visible tiles clear. View shed visible tiles equals field of view point Y. That's the same. And then we have same. Believe that's the same. All right, so now this is the new code. All right, so we say let p, which is an option. That's a new thing that we're using. And player.get. All right, what the heck? Okay, so this is using. Make sure. Yep. And then we have let sum p equals p. Wow, that's weird. Let's put that in parentheses. Okay, it doesn't like that. So this one here cannot be wrapped in parentheses. Love it. For viz and viewshed dot visible tiles dot iter let idx equal map dot xy idx visible dot x visible dot y map dot reveal tiles idx should mark it as revealed now. It does. All right. Everything stays green. Cool though. That's really cool. I don't know what the map looks like until after I've explored it. That looks great. That looks really cool. Alright, so the main changes here are that we're getting the entity list along with the components and obtaining read-only access to the player's storage. We add those to the list of things that iterate in the list, and we add let p option player get entity, to see if this is the player. The rather cryptic if let sum p only runs if there is a player component. Then we calculate the index and mark it as revealed. If you run cargo run the project now, it's massively faster than the previous version, and it remembers where you've been. Speeding it up even more, recalculating visibility when we need to. It's still not as efficient as it could be. Let's only update view sheds when we need to. Let's add a dirty flag to our view shed component. Component. Pub dirty. Easy peasy. Also update the initialization of main.rs. Yep. And it probably needs to be true by default. Yes. Okay. Our system can be extended to check if the dirty flag is true and recalculate it if it is, and set the dirty flag to false when it's done. Now we need to set the flag when the player moves, because that's because what they can see has changed. We update the try move player and player.rs to get the mutable view shed. Yep. Let mute view shed ECS, and I'm not looking at the other screen. Right, storage, and this should be shed. Okay. And then over here, when we update the X and Y position, we say view shed dot dirty. That's true. Perfect. That's okay. This should be pretty familiar by now. We've added view sheds to get the right storage and include it in the list of component types we are iterating. Oh yeah, we did. We did add it up here. Sheds, plural. Awesome. The game now runs very fast once more. If you type cargo, I don't think it's ever. That's true. But dirty never gets changed to false. Never checking for dirty here. Never gets changed to false. Alright. So we'll say if viewshed.dirty run this code, and we'll say viewshed.dirty equals false. Run it, make sure it all works. Yeah. Nice. Okay. This should be pretty familiar by now. We've added view sheds to get the right stores included to our component list. Yeah, that's true. You never actually updated the visibility system to actually use it. Oh, look, now they're doing it. Okay. I guess they wanted to do the refactor of graying things out first. But, we'll just flip the order here. Okay, one more extension. We'd like to render the parts of the map we know are there but can't currently see. So we add a list of tiles, of what tiles are currently visible to the map. Okay, visible tiles, .rs, revealed tiles, and we'll say pub visible tiles, and this will be vec full. Okay. Station. Our creation method also needs to know to add all false to it, just like before. Visible tiles, vec false. Okay. Next, in our visibility system, we can clear the list of visible tiles before we begin iterating, and mark currently visible tiles as we find them. Okay. Visibility system. Okay. So viewshed dirty, viewshed dirty false, visible tiles clear. Go to view stuff going on, and then we have that retain function there, and then we'll say player reveals option player underscore p. So we'll just leave this the way it. Okay, apparently underscore p underscore p. No, because we are using. Does it all have to be underscores? Okay, whatever. That is what it is. So now let's see here. Have underscore p player get entity. Let sum p equal p. For t. Okay, they're doing. What does T stand for here? For tile in map visible tiles dot iter mutable tile equals false. And then we can actually say map revealed tiles, map dot visible tiles x equals true. Now we adjust the draw map function to handle revealed but not currently visible tiles differently than the new draw map function looks like this. Okay, so we have let idx. Yep. That's correct. Save that with a draw map function here. We say map mutable x and y, idx tiles iter, enumerate, render a tile dependent upon the tile type, map reveal tiles idx. We let the glyph let mute fg, and we say okay. So this is that. Okay, that's fine. That is just below the say if map dot visible tiles x fg equals fg dot to grayscale. Okay, that's fine. This probably needs to be into I prefer to do if statements. You can actually I misspelled cliff. That's funny. All right. So we have floor and this glyph equals RLTK dot to CP and we'll throw the hashtag down here. Then here we say FG equals RGB from F32 0.5 0.5. Okay, these numbers apparently have changed slightly. Alright. And we'll do the same thing down here. 0, 0. I do 1 point. Yeah. That's fine. And here we're doing the CTX set, and this is FG, the first parameter here. And then the last parameter is that glyph. Awesome. Now what happens when I run? That actually looks really good. For some reason, that particular map, I guess, I don't know, I've got a wall in the middle. Oh, yeah, it's 2 corridors, that's why. That's cool. Okay. If you cargo run, your project will now have visible tiles as slightly cyan floors, and gray will move out of view. Performance should be great. Congratulations, you now have a nice working field of view system. Yes, it actually looks fantastic, actually. I would almost like this to be even lighter gray. So stuff that I really can't see, it's very light. Just this 2 grayscale functionality. I will leave it the same for now. Um, Actually, no, let's change it. So we can say if map dot visible tiles idx case foreground else, and this is the floor, right? So we'll change this to like 0.15. That should be gray, a very light gray. And then the same thing for the wall. We'll do the same thing here. Say foreground is that by default, and we'll actually, we don't even need to do this. We can actually just, rather than using the 2 grayscale, because I want everything to be very light. I can actually comment that out there, and this a rerun. Yeah, because I want things that, yeah, see that? I think that looks a lot better. Stuff that you can't see, it's very dark. I want the game to be very dark. We can go even darker if we wanted to. At this point I'm just playing around, but I think it looks really cool. Okay, so we got this game working. It's not identical to what the tutorial has, but I think it looks really nice. Very dark looking game. Okay, cool. Um, Thank you guys for watching. If you want to see more of this kind of stuff, go ahead and hit that subscribe button because I'm filming this whole series. The next episode, it looks like we're going to be getting into placing some monsters down on the screen and stuff like that. So yeah, thank you for watching. Have a rest of your day. Bye bye.